Thank you, Brian. Thank you very much. Our last speaker on this panel is going to talk to us about more futuristic things, I think. It's John Freese. He's the Design Director of Product Development Technologies in Newton, Massachusetts. John.
Thanks, Karen. Thanks for having me here. First, I'll give you a little bit of background. I'm a mechanical design engineer and a leader of teams. Yeah, it is. No? There it is. How about that? Hello, hello, hello. So, as I said, I'm a mechanical design engineer and a leader of teams that develop electromechanical products for volume production. I've done everything from mobile phones to kids' toys to medical devices. I work for a company called PDT, which is a product development consulting firm. We've got 130 employees around the globe, and our niche is developing rugged mobile electronics. About 3 years ago, I approached Braille as a complete outsider. I'm sighted. I didn't know much about Braille at all, but through work for Perkins and something called the Transforming Braille Group, I think I've seen a good sample of current technology and what could come next, while still hoping to be surprised by something new, like Brian's talked about. So Judy Dixon asked me to talk on why we haven't seen much change in refreshable Braille cells in the last 30 years or so. Curtis talked about it, Jim and Brian talked about it as well. You know, Judy said, why is it so hard to find another way? And my answer is actually pretty short. Improvement is only constrained by size, weight, speed, power, cost, noise, reliability, and production volume. So just because the answer is short doesn't mean it's simple. And as an engineer, I'm sort of the bad guy to say that it's not magic, that it requires a lot of work, that current piezo devices may cost too much and they require more maintenance than desired, but they actually perform pretty well across those criteria when used in a single-line device. So let's look at these critical success factors and talk about them a little bit. Cost is a given. Everybody wants lower cost. But size of the Braille dot is probably the biggest issue in finding a way to improve on piezo cells. Even though we're starting to see haptic QWERTY keypads, these are on text letter keys that are probably 50 times bigger than a Braille dot. So scaling down to a touchscreen haptic output to the size of a Braille dot, even though it may be theoretically possible, is just too big a leap right now when we're just getting into production with something that's 50 times the size of a Braille dot. Even the smallest tactile switches and keys are still 5 to 10 times larger than a Braille dot. So finding something to meet the Braille standard is therefore forced to be some sort of micro-sized mechanism, and mechanisms mean complexity and cost. Power consumption and portability is probably the next largest complicating factor. Alternate materials and mechanisms often require inefficiently high voltages or fans to cool them to meet the speed and reliability requirements that you're used to. This means a bigger, heavier battery or even a plug into the wall, and I don't think anybody really wants that. I've seen lots of concepts that try to get around the size issue by moving mechanisms and electronics away from the small outline of the cell itself, but that hurts for portability and complexity. Reading speed. Reading speed is controlled by the reader in existing RBDs, but they can react very quickly for fast readers. Refresh rates under 300 or 250 milliseconds are quite hard for complex mechanisms and some alternate materials. Maximizing speed tends to cause higher temps, require more power, and increased noise. Noise is a possibility anytime something moves, especially when it's moving quickly. It is something we're all sensitive to, especially when trying to read in a group. Piezo cells are very quiet and will likely take something similar that doesn't use motors or gears to keep a next generation device quiet. Next is reliability. Piezo devices certainly do require care and maintenance, but they can provide the necessary millions of cycles if kept in good condition. Many alternative cell ideas driven by motors or solenoids just can't meet that high millions and millions cycle requirement. Development cost and low production volumes are huge behind-the-scene issues that most users don't see that keep new concepts from getting to production. It's a bit of the age-old chicken or the egg question in that truly novel new technologies need lots of upfront capital to develop and therefore a big volume payoff once in production. RBDs are still too much of a niche product to draw that kind of attention, so we have to try to find something that rides on the coattails of other advancements. Obviously, any haptic tactile advance is of interest to this community, but as I mentioned, a lot of these simply can't be applied yet to something as tiny as a Braille dot. Despite what I've said, you're likely still sitting there saying, wait a minute, I was reading basically the same piezo cells back when Reagan was president. Back then, every phone call I made was from a rotary dial telephone that was anchored to the kitchen wall. I've got an iPhone now. This is crazy. Come on, give me something better. So let's compare RBD cell hardware to that of the iOS devices that everybody loves so much, and I do too. The very first music iPod was a clunky brick that had a mechanical scroll wheel tactile interface and a tiny black and white, totally inaccessible, non-touch display. It was thought of as weird because the user couldn't take the battery out to charge or replace it. But improvement in hardware and software has made iOS devices almost completely solid state with no moving parts. This is a huge advantage in all the criteria we've talked about. Smaller in size, fewer components to wear or break, no noise, less power means less heat, plus, of course, massive production volumes to cut costs further. Your iPhone is a solid physical object which mechanically doesn't have to do anything except maybe vibrate stupidly every once in a while. But the RBD still has to push up the same dots millions of times to mimic what you would feel on paper. The reality of product development is that most products fail to catch on and are forgotten. Not to get too philosophical on you, but we need to fail a lot before we can make real improvement on something that works decently well. What is critical is that we need to make sure that all of the many well-meaning, and in a few cases well-funded, efforts to improve on the piezo cells aren't forgotten, but in fact are built on and learned from. From talking to many longtime Braille users, I know that a lot of global effort has been spent trying to get the same idea to work over and over again. The team I've worked with on the Transforming Braille group is trying to spread that information so that at least others will be aware of what has been tried previously so that we can be efficient in our resources. So now you know all the excuses for why nothing has replaced piezo cells. What does this mean we can expect in future Braille technology? Of course, I can't know for sure, but I would categorize likely future developments in three groups. First group, cost reduction and modified use of existing piezo cells. Examples are new products from APH, NBP, and others that push lower cost in other components and or use fewer cells while still hoping to grow the market to push piezo cell volume up and hopefully drive them further down the cost curve. But piezo costs will only come down if there is competition from other types of cells. The second group is what I would call novel use of existing materials in new mechanisms. These will tend to be complex workarounds by clever and motivated mechanical people who don't listen when someone says, "It'll never work." These new mechanisms are prone to compare badly to piezo cells in at least a couple of the critical factors we've talked about, just like Brian mentioned. But they can still be successful in the market as long as users can accept the benefit trade-offs with the fact that they'll fall short of piezo on speed or noise or portability. The focus of a lot of these concepts is currently on multiple line or full page displays because it is so tough to beat piezo for a single line unit. The third group is, as Brian mentioned, based on new material science to develop electronically controlled polymer actuators. These are materials that are trying to more directly and efficiently turn electrical input into movement using more solid-state control approach. Most of you have heard about the potential of these EAP concepts for years as they've been in development for a long time, but some are really getting much closer to getting to market. And why? It's because demand for high-volume mobile haptic devices that could help drive costs down below piezo while matching or improving on other criteria. These materials have taken lots of time and money to develop as well, so they will still have patent protection and at least some cost issues to start, but should offer lower cost once they're designed into high-volume devices by the big boys of tech. Believe me, if Apple comes out with a haptic keypad on an iPad screen, they will be only doing that because they've gotten the cost down to where they can make a nice profit for all their shareholders. So, could a product from one of these three categories be successful in bringing lower cost RBDs to market in the short term? I certainly hope so, and I'm sure they will. In the longer term, could something even more advanced get developed that doesn't fit into these three general categories, but still promotes Braille literacy? Absolutely. As a thought experiment, let's try to set aside at least a few of today's constraints on new Braille technology. Given that we are approaching a point where it may be possible to sidestep the need to be constrained by paper, maybe the long-term answer isn't finding a way, or the long-term answer is finding a way to use the Braille code language developed with such effort in new ways, not dependent on tiny dots on a piece of paper. Given that the greatest step change in electronics has come in moving to solid-state components and better user experience, why not tailor a jumbo or alternate size Braille cell size so that each dot can be felt haptically? Then maybe a palm placed on a flat touchscreen could feel imaginary tactile dots of Braille. Or we could teach readers to recognize a larger Braille cell output through 6 vibrating motors laid out in the palm of a glove when you point a finger at a letter on the screen. Those are just a couple quick ideas that likely aren't even that original. The people in this room are not only Braille users, but the stewards of its future, so I'm looking forward to hearing even more crazy ideas in the breakout sessions. Thank you.